It's all right. So once again, welcome everyone to today's IAIFI Colloquium. It's a quite unusual event. We started 1 hour earlier than usual, and we are here in Kempner today to have this mix and chat and close interaction between IAIFI Institute and Kempner Institute. And we start today's session with our usual colloquium. Today we have let's say Kempner postdoc Andy Keller here with us. Is going to talk about flow equivariance. After the talk, we are going to have a mixer session, like half an hour of chat and conversations with some food. So please stay until the end and enjoy the conversation. And yeah, I'll just leave the floor to Andy for flow equivariance.
Thank you, Gaia. Okay, so yeah, I'm just going to say the point of the talk is to hopefully make you guys think about new ideas, come up with interesting connections, not so much the usual, like, I'm trying to convince you that everything I'm doing is incredibly practically relevant and useful in your daily lives. Because I typically enjoy talks where it makes me think of new ideas. So hopefully I can do a little bit of that for you. That being said, we'll get into it. So, okay, a long time ago, back in the 1600s, right? But it's actually not that long ago when you think about it. The Earth was believed to be at the center of the solar system, the universe, the planets, and the sun, the stars. That being said, we'll get into. Oh, okay. With the planets and the stars orbiting around it. And one of the common arguments for this was this idea that if you're, for example, in a moving frame, if you're on a boat or something like that, and that boat has some forward velocity, and people said, okay, if I drop something from the top of the mast of this boat, I'll see it move backwards, right? Like it kind of like has this trajectory because the boat is moving underneath it and the thing moves back like that. But if I'm on a tower on the Earth and I drop something, I see it fall straight down, right? So we must not be moving. The Earth must not be moving. We must be stationary. So in 1632, Galileo wrote this book on dialogue of the celestial bodies, something like this, where he basically tried to argue against this as one of the potential arguments for why the Earth is at the center of the solar system. And his argument was that whether you're in a stationary frame or a moving frame, the ball will actually fall straight down. It will undergo the same laws of motion no matter what your state of motion is yourself in an inertial frame. And so basically you can verify this really simply from just looking at the coordinate systems for these two boats. So one is stationary, one is in motion with a position coordinate that's indexed by z with a minus vt. T is time, v is the velocity of this boat. If you look at the equations of motion, so Newton's second law, F equals ma, where your acceleration is the second time derivative of your position. If you look at your coordinate system that's in motion, z prime, you take the time derivative, this t drops off, you take a second time derivative, all you're left with is z. So your acceleration in both frames is the same. Your force in both frames is the same. So essentially what Galileo was saying, even though this hadn't been introduced yet, this was before Newton, what he was saying is that the laws of physics are invariant to your change of reference frames. All of the laws of physics should operate the same, whether I'm moving or whether I'm not moving. The thing I wanted to say was, when people were making this argument that I showed here, they had claimed that they had observed this effect empirically on boats, dropping stones and things like this, and that they moved backwards. And it turns out that Galileo actually had to go on a boat himself and run this experiment to effectively prove people wrong and show them, no, that's not what happens. The things fall the same whether you're on a boat or not. Okay, so this was his argument. And this was kind of the first introduction of relativity called Galilean relativity, not the same as Einstein's relativity, but the same conceptual idea that the laws of physics should be the same no matter whether you're in a moving reference frame or a stationary one. This had huge impacts, right? So one, the sun is at the center of the solar system. 2, we get things like general relativity all the way up to the physics that I'm sure people here can describe much better than I can. So what I've been thinking about for a while is how do we think about these ideas in terms of neural networks? How might these ideas apply? And it turns out the connection is relatively simple. And it comes from this field of equivariant deep learning, geometric deep learning. And so the simplest example of this is a convolutional neural network. The idea being that equivariant neural networks in general have this property that they should operate the same in any reference frame that they're equivariant with respect to. So if I transform my input, I move my input to a different frame, this should be the same as just processing the input as it was originally and then transforming the output. So for a convolutional neural network, this is if I have an input like this image F over here, and then I shift it, so I get this shifted version of the F, and then I pass it through my CNN, this should be the same as if I pass the original image through and then transform the output. And the way you can think about this in terms of reference frames is that maybe in the original setting, I have this coordinate system that's in the lower left corner of my image here that we call Z, but there could just as well be another coordinate system that's shifted over to the left by some number of pixels. And we want our network to basically operate the same in that alternative coordinate system, right? We don't want something weird to happen to this output. We want it to just operate exactly the same, but with this corresponding shift. And so what does this equivariance property buy you? What does this property of like operating the same in different reference frames give you? It gives you robustness to these types of transformations. It means your output space is structured with respect to these input transformations. So this is the first paper that introduced the CNN, by neocognitron by Fukushima in 1980. And you can see the whole point is to build something that's unaffected by a shift in position. That's why this thing was introduced. So if you move your image around a little bit, your output changes in a nice predictable way. And so this isn't just limited to translation. People have built equivariance with respect to other types of transformations. So this is the translation picture I was showing you before. This is for rotation. So this is a group equivariant convolutional neural network. And the basic idea is still the same. If I transform my input, this is the same as transforming my output. There's this corresponding map. But you can see when you get more complex transformations, you get a little bit more complex formulation of how the network is built. So for this rotation equivariant network, you now have your weights tied for your convolutional filter. You can see it's a rotated copy of my convolutional filter. And this is what's called lifting the feature space to the group dimension. So this is for a group of 90-degree rotations. We've lifted this original feature up. You can see we still have the original feature, but now we have these 4 other versions of that feature that are the corresponding rotated versions of it, so to speak. And you can see that because of this, the action of the group transformation in the output space is no longer exactly the same as it was in the input. So previously in convolution, shift of input is shift of output. Now we have something more complicated for rotation. The rotation of the input corresponds to a spatial rotation of the output, but also a permutation of these rotation channels. And if you go through the example, just looking at like this feature now hits where previously it was this feature, you'll see that it makes sense. Okay, so again, we have this equivariance relation. These are these commutative diagrams that I'm going to show to try and emphasize how we build equivariant networks and what it means to be equivariant. So just to give another example, we can like think of rotation equivariance in terms of processing the same input in 2 different rotated reference frames. So a regular convolutional neural network processing an input that's in a bunch of different rotated reference frames. You can see the feature map, if we undo that rotation, undergoes this weird kind of unstructured transformation, right? So this means if I'm looking at a face like this or a face like this, the output's going to be very different. However, if we build a rotation equivariant convolutional network, you can see that the stabilized feature map is solid, rock solid, right? And actually there's little vectors on here. I don't know if you can see them. These correspond to that 4-dimensional state I was showing you before. This is that direction of that vector. And so these little vectors are rotating in correspondence with when the input rotates. Okay, so equivariance works generally. You'll get data efficiency benefits, you get generalization benefits. This is why people use convolutional neural networks, right? You can build it for rotation, you can do convolution on manifolds with these ideas. You can use it for trajectory prediction, for self-driving cars, for reinforcement learning, diffusion MRI, and maybe most famously, I think in AlphaFold 2, they used it for protein folding. It's used a lot in like molecular simulations. And you can see that it makes sense because no matter how this protein is oriented in space in 3 dimensions or translated around, it should still fold the same way, right? Your solution space is the same. You have this symmetry of the solutions with respect to this group of transformations. And so it's very helpful to build that in a priori so your model doesn't have to learn it, especially in these like physical settings where the symmetry is exact. So that was all kind of like the past stuff. But there's a missing piece here that I think is relevant to the type of machine learning that a lot of people do today. And I'll say that that existing past work is typically what you would call a static symmetry. So the idea being that you just have an input and that input is transformed. There's no notion of sequences. There's no notion of time. In some settings, people have applied equivariance to sequence models, but they still do it in this kind of static symmetry setting. So you have the same group element applied to every element of the sequence, and you can see that it's the same transformation that's being applied over time, right? So in the self-driving car example, you would say my car operates the same, whether the world is like this or the world is rotated like this, but that rotation is not undergoing a change over time. It's just a static thing. Alternatively, this is what I call a static symmetry. The thing that hasn't really been covered is what I'll call a flow symmetry or a time parameterized symmetry. These are symmetries where you have some time parameterized transformation that changes over the sequence length, right? So here you can see now there's an actual motion of this person's face, who you may know. So why are these time parameterized symmetries important or interesting? What I'll say is that intuitively they dominate our natural world, right? You can imagine just walking down the street, things are moving smoothly. Even I'll go into a little bit later. Moving in the world induces these types of transformations on your visual field in terms of optic flow or things like this. But also, I think a more salient example is generative video models today. So these are examples from VO3 that was, or 3.1 that was just released recently. They're mind-blowing, right? These are all generated videos. I still can't believe that this is real. These are from the original website. And you can tell they all look beautiful, right? And they look perfect. And so you can see like here, the motion of these bears, I would call like as a smooth flow type of symmetry, right? But I would argue that the output of these models generally is maybe not as beautiful as these examples that they put on their website. So I went and I was using VO3. The very first prompt I put in was a gymnast doing a flip on a balance beam, because this is known to be a challenging problem for these models. And this was what came out. You can see her head kind of flips backwards there, and then she's back. Her body did some weird like inversion halfway through. So, I mean, obviously this is incredible, right? Like there's a screen up here that's matching what's going on down here, but there's still these weird properties that are not how we intuitively would imagine a video happening. And I argue that these are actually these time parameterized symmetries, right? There is something that's constant in the world, maybe her body pose position, which is undergoing a smooth transformation, and that's just not being respected by these models. So, can we fix this in some way? How do we build equivariance to these types of flow symmetries? So I'm going to say maybe we take inspiration from the relativity ideas, this idea of inertial reference frames as a starting point. Don't take it too literally, but I'm also interested in that. So equivariant neural networks are doing the same processing in different static reference frames, like I was arguing before. This idea of relativity is the laws of motion, the laws of physics are the same in all inertial reference frames. Maybe we should build equivariant recurrent neural networks that do something like the same processing in all inertial reference frames, right? This would be one way of thinking about this. So what is an inertial reference frame? This is the simple example. You're in a train looking out the window, the world is moving by. You can think of this as your coordinate system is in some moving coordinate system, which is parameterized by time. So what does it look like for an RNN? If you have a simple RNN here, this is your hidden state. It's a vector at time t. You have some linear matrix for your hidden to hidden map and also for the input to hidden map. So your encoder and your hidden state are linear and maybe some ReLU nonlinearity. If you look at something like the input here, discretized over space. So again, this is this one-dimensional vector, but now we're plotting it as if it were continuous, but you can also think of it as like 50 independent values. This vector is going to have some time component to it as well. So you can think of this as a sequence over t time steps. And so if we plot that as a little movie here, that's what these look like. So then this vector in a moving reference frame. So if we apply what we're calling this like Galilean transformation that shifts u of t by vt at every time point, we'll get something that looks like this. So this is an input, a one-dimensional input in a moving reference frame for something like a recurrent neural network. So what would it mean for a recurrent neural network to have this Galilean equivariance property? So equivariance to this shift. Well, if we have our input sequence u, if we shift it, we get just a moving copy of it like this. And then we process that with our recurrent neural network. We get some sort of output. What we want is that if we process the original static version with our recurrent neural network and then shift it, we should get the same thing. And you can see in this case, it looks like we do, right? These two versions are shifted versions of one another, I think. So the idea is that RNN should work the same way in all of these inertial reference frames. And basically we get this same commutation relation that I was talking about before, where if you shift the input, it's equivalent to shifting the output. Okay, so the first example I'll go on is a linear recurrent neural network. And please feel free to interrupt at any time if there's questions. A simple linear recurrent neural network with these dense weight matrices is obviously not equivariant with respect to something like a translation, right? And the simple fact, you can see that from an arbitrary weight matrix is not going to commute with a translation operation. So if we plot here, the dashed line, I'm basically just showing this plot here. So the dashed line is going to be this, going along this path, and then the solid line is going to be going along this path here. And so ideally they should line up if we have this equivariance property. What we see is for the linear RNN, they definitely don't line up. This is the input down here, and then this is those two paths. And so the idea is, okay, somehow the encoder or the recurrence are not equivariant here. So what if we make both of these operations convolutional? So now these things do actually commute with this translation operation, at least in a single time step. So if I translate the input, this is the same as translating the output of the convolution. This was exactly that first figure I showed. And you can see it's better, right? They're almost matching up, but as you start to get higher variance in this hidden state, they diverge at some point. What we want is something where they're exactly matching the same, right? How do we get that? So I'm going to show a little video here which shows you why this problem is happening, a really simple example, and that'll give you intuition for how we build something that avoids this. Okay, so, oh wow, this is really low contrast. This is the input down here. It's going to go through an encoder to produce some encoded output like we were showing before. This is the hidden state at time t. These things are going to be added together, right? This is just the simplest possible RNN, and that's going to go to the next hidden state time step here, which is then going to move back, and it's this loop, right? This recurrence. Oh. And so this input is going to be undergoing a flow transformation. It's going to be moving at every time step. And then it gets combined with the hidden state to form the next hidden state for the next time step. And then we move it back and update our timer. And what you can see is that the input is basically always one step ahead of where the hidden state was, which makes sense, right? The hidden state doesn't know what's happening with the input, and the input is always moving. So instead of getting this nice, smooth flow of your output like we wanted, you get this kind of smeared version of the bump in your hidden state. And people call this like your RNN integrates information over time. But I would argue you're integrating information in the wrong reference frame, right? This hidden state is static, but your input is moving. And if you really want to process the input kind of in the same way, maybe you need to do something so that you don't get this smear and instead you get a smooth moving bump. Okay, so to show this a little bit more mathematically, if we take our RNN equation and we abstract it to just a function of the hidden state and the input, we want this commutation relation like I was talking about before. If we write out the two sides of this equation, the left side of this equation is the transformation of my hidden state. Since this thing commutes with our nonlinearity, like a pointwise nonlinearity like ReLU, and also commutes with the convolutions like we talked about before, we can just push it in here. So this is the left side of our equation. The right side of the equation, we have a transformation on our input, and it's only on our input. It's not on the hidden state. So we can see these two equations don't match up at all, right? And the culprit is this term. On one side, we have a moving hidden state. On the other side, we don't. And so we're missing this motion in the hidden state, like I was trying to point out before. The hidden state is not in the same reference frame as the input. So how do we fix this? Well, we basically just add a flow to our hidden state that corresponds to the flow in the input. And I've written that up there as some additional flow that's operating on the hidden state. So we can visualize this now. The input comes in, but then before we add in the new input, we shift our hidden state. And now we see everything lines up, and our sequence of hidden states is now this bump that's moving in correspondence with how our input is moving. Okay. So that's the secret. It makes things work. We see it works better than this convolutional RNN again. No surprise. Why does this work? I'll go over a proof here, not because I think it's important and you guys should be interested in it, but just because there's two key steps which are going to motivate the whole construction of this thing. So again, this is our Galilean equivariant RNN. Our hidden state is a function of the sequence of inputs over the past time. And then we have this shift here. And I'm changing notation a little bit. Previously I was using psi, now I'm using gamma, but we'll stick with gamma right now. Okay, and this shift is just this x minus vt operation like we were talking about before, and the goal is to prove that shifting the input is equivalent to shifting the output. We do this by induction since it's a sequence problem. So we're assuming the inductive hypothesis that this holds for time t minus 1. We want to prove it for time t. So here we're just writing out what the shifting of the input looks like for this RNN equation. I use the inductive hypothesis, which means I can pull this gamma from inside the H to outside the H. But now we see that, okay, we have our gamma t here, which is what we want, but here we have these two terms. We have gamma 1 and gamma t minus 1. So we have to use this property. We have to assume that what we're interested in has this property that a shift of time t minus 1 plus a shift of 1 equals a shift of time t, right? So these flows should combine over time. They should be additive in that sense. That combined with the fact that we want to pull this through the convolution operation gives us the proof. So, okay, this works, but there's two caveats. This only holds for a single velocity like I was showing before. If the hidden state is moving at a given velocity, that's the only velocity that it can track for the input. And it only holds for translation right now, which is like, both of these things combined make this entirely useless. So how do we generalize this to more complex transformations and fix some of these problems? So beyond translation, we want to leverage the most general form of a transformation that we can that has this property, which I call this additive flow property. And the second thing is we just need to be able to move this transformation through this convolution here. And you can do that by using group convolutions. The second part is we're going to do the same trick that people did for rotation equivariance that I was showing before, where you lift your state to the group. So we're going to have multiple different velocity channels that are all moving at different velocities to achieve equivariance to many simultaneously. Yeah.
Yeah, haven't used an inverse, so you can do a semi-group.
Yes. Yes, you can do scaling, I believe. Actually, you're right. In this proof, I don't use an inverse, but I would have to look at the actual proof. I think you can. Yeah. Okay, so this property, this additive property is a property of flows. So formally one parameter subgroups, Lie subgroups of general linear group. So some matrix exponential of your Lie algebra element. So you can think of this as like a little vector field. And the action of this group element is what we call a flow. So it's a mapping that takes in the vector field and an amount of time and gives you the basically how far you're supposed to move according to that vector field in that amount of time. So it gives you the corresponding distance or the group element. You can think of this as like a path line, and you drop a drop of dye in a fluid or something like that. At each point in time, it's going to take you to a different position. These are these flow things. So translation flow for some amount of time basically just does this translation like we were talking about before. You can have rotation flows, where now the action is a little rotation matrix on your coordinates that's identified by maybe like the rotation, angular velocity, something like this. These are just the simplest possible examples. You can come up with many more semi-groups that you're saying scaling or coloring if you're doing like a color rotation in hue space or other types of transformations like this. Yeah, I won't go into the full set of things that are covered here. It gets complicated, but I just did translation and rotation. I'll leave the rest to other people. So the one velocity problem, how do we fix this? Well, like I said before, we basically just want to duplicate our hidden state or lift it to the group. So we're going to have a lot of these different flow generators that are indexed by V in this example. And this is analogous to rotation equivariant networks. Instead of just having a single convolutional filter, we have rotated copies of our filters, which correspond to this, basically the full set of group elements that we want to be equivariant with respect to. So all of the rotation group, rotation by 90 degrees. So our hidden state can be seen as stacking all of these different recurrent operations where they're sharing the same weights, just like the rotation CNN is sharing the same convolutional filter, but there's a difference in how the recurrence is operating in that every channel basically is flowing with a different velocity. And then to achieve some sort of invariance to flow velocities, we can max pool over that dimension at the end, or we can keep it around, just exactly the same as with equivariant neural networks. So now our hidden state is defined on this product of the original space, which we're calling G. You can think of it as like spatial dimensions, neurons, combined with this kind of flow dimension. So this is like different velocities of flows and things like that. Okay, so what does the full flow equivariant RNN look like then? I'm not going to go into this because you guys don't really need to care about it, but basically it's the same as before. We have the flow that's applied to our hidden state. We're using a group convolution so that we can do this pulling through the hidden state. The basic idea is if you want to be equivariant to some flow transformation, both your encoder and your recurrent processing need to be equivariant to the instantaneous transformations of that thing. So like a rotation or a single translation. And then this just does a single step of that flow in that sequence. And what this gives you is that if my input is transformed by some velocity, your hidden state, what happens to your hidden state, this is that latent operator I was showing before, ends up being a flow of the spatial dimensions that's given by that velocity, but also a shift of these velocity channels corresponding to the relative velocity difference between the input flow and that channel's flow. So what does that mean? If I have this bump example, again, so this is a stationary bump, and it produces this type of an output in that model. So you can see this channel is moving to the right with velocity 1, this channel is stationary, this channel is moving back with velocity 1. If I now shift my input, the corresponding transformation up here is that my hidden state shifts up. So you can see this guy here that was previously processing the static input is now processing this moving input as if it were static, but in this moving reference frame. So you can really think of each one of these channels as like seeing the input from a different moving reference frame simultaneously. and then they're able to process the input in a structured way, and you get this nice structured transformation in the output. Okay. So what can we do with this in practice? What does this yield? Let me see, how much time do I have here? 20 something. If we plot these videos like I was showing before, instead of as these time series, but as a space-time plot here. So you can see this is the same thing that we're seeing here, but time is just plotted on the y-axis for simplicity. If something's moving, it's going to have this tilt to it. The equivariance property is going to look like this. If my input tilts, I want my output to also tilt. We're going to train an RNN on a really simple signal detection task. So again, this is the signal over time. And what we want the network to be able to do is to identify when there's like a bump in that signal. So is there some sort of peak in that noisy signal compared with these examples that don't have the peak in it? So we train it on a lot of these just binary classification examples. And then at test time, there's a signal where there's a moving bump and it's never seen a moving bump before. So a convolutional RNN just fails miserably at this, right? At train time, it's achieving perfect accuracy. At test time, it's basically at chance. Whereas if you build in these velocity channels and you max pool over them as expected, you basically get this perfect generalization to these velocities that it's never seen before. And we can visualize this, that shift I was telling you about before. These are the different velocity channels, -2, -1, 0 velocity, 1, 2. So that the model has seen the input come in at something like a 0 velocity channel here. This is a static input being processed by the network. Then the input starts shifting. This is what we're getting in the output. We see that the thing looks like it's moved to this velocity channel. So we can shift it back and then compare it with the input, and we see that the difference is basically 0, except for this one channel at the end here, which corresponds to when we shift this back, we don't know what's at velocity 3, right? So we can't match this boundary. So this is one of the main problems with this current architecture, is that we have to pick a priori a set of velocities that we build into the model. And you get these, we're kind of truncating this infinite dimensional velocity group to a specific range. And so when you do these kind of shift operations at the edges of that group, you're going to have errors. So that's where this is coming from. Okay, so real data. MNIST. So we have the first task that I tried this on was a simple flowing MNIST data set. So you have MNIST digits. In this case, they're both flowing in the same direction at the same velocity, but in the data set in general, they're flowing in random directions and random digits. And the task of the network is it sees some number of frames, I think it's 10, and then it's required to predict the next 10 frames autoregressively. So it feeds its output back into itself and predicts the next 10 frames. And so if you do this with a convolutional neural network, it's basically able to do it for the training length. So here, these are the feature maps of the convolutional neural network for the training length. And then you can see it slowly starts to degrade over time. And similar to that rotation example, I'm stabilizing them here so you can see it kind of like dissolve. It's kind of cool. If we look at this flow equivariant network, the hidden states are, again, like rock solid. And the reason is like the network is processing this input as if it were stationary, right? It's in that moving reference frame, at least in one of its channels. So there's no reason that it should change, right? It's just seeing the same thing over and over again. If we look at like training speed, so on translation and rotation, these things train way faster. This is if you have equivariance, so single velocity or velocity ±2. We can also generalize significantly further in terms of like length extrapolation. So this is the training length again, and then we're trying to predict out like 70 so steps in the future. We see the regular convolutional RNN starts to dissolve, whereas these flow equivariant models are able to handle this perfectly. This is plotting over time steps, how those two curves look like. The error, you can see the error on the convolutional RNN is just massive compared to our models, which are relatively stationary. And the same thing holds if we do this for multiple digits. We can see that the equivariant model basically has zero error out into the future. And the reason for this is we built in this time composition property of flows. So you naturally get this generalization to length with this kind of like flow symmetry in your recurrence. I thought this was really cool because this is a property that you don't see in general equivariant networks, right? There's no notion of sequences or length or anything like that. Something you do see in equivariant networks is generalization to group elements. So for example, if you're training on rotated MNIST, but your data set only contains a certain set of rotations, but you have an equivariant network that's equivariant to rotation, you'll get generalization to all rotations simultaneously because your weights are tied. We see the same thing for velocities. So the network's only trained on velocities plus or minus 1. You can think of this as like little vectors and -1. The GRNN, when we test it on velocities outside of that, has massive error, whereas our model doesn't because we've built those in to the model. And we can do the same thing for rotation. We train it on plus or minus 10 angular degrees per second or per step. We build in up to 40, and we see that we have very low error, whereas the GRNN immediate or the regular conv RNN, call it GRNN, starts to fall off very quickly. Something that everyone always asks me is, okay, you have a discrete set of velocities. So for example, we pick -1, -2, up to whatever, 5. What happens if your actual flow lies somewhere in between those velocities? What I found in practice is that these models can some extent interpolate between those. So the green bars are the original model. This is the error of the model when we're testing on a set of velocities plus or minus 5. The purple bar here is when I built all of those velocities in. So you see it achieves relatively low error, but then this pink bar is missing, for example, 2 and 4. But we see on 4 and on 2, the error is not that bad, right? So it's able to interpolate in between 5 and 3 to kind of still be able to model these velocity 4 transformations. And this is something that's seen in equivariant networks generally. Even if you discretize the group, you're still able to achieve approximate equivariance to elements in between those discretizations. Okay. I'll go over really quickly. This was this world modeling work that we did with this flow equivariance idea. This was work by Hansen, Lil Mark, who was here for the summer, and Ben-Hao Wang. They did an amazing job on this, and the idea was if you're doing a world modeling task, specifically a partially observed world modeling task, things in the world are going to be moving potentially behind you or in front of you, and you're also going to have like a limited world view, and you're also going to be moving in the world, right? So how do you integrate all of this information simultaneously to be able to predict? So you see the world for some number of states, and then at some point it stops, and you're only giving your actions between time steps. How do you predict what your future observations are going to be? So for example, on MNIST world, there's a world state. You see some like limited window of that world state. You take an action, but then the world also evolves while you're not looking. And then you get another observation. So you moved up, your little window moved up, but you can see the digits also moved a little bit and you get a new observation. At some point, you stop getting observations, you only get actions, and you have to predict your future world states. So what we do is we take this original flow RNN equation, and what we observed is that action of things in the world, which is what this part was originally covering, is equivalent to the inverse of my own action, right? So if something moves like this in the world, that's equivalent to me turning my head in the opposite direction. So what we can do is just add an extra term to this flow, which is the inverse of my own action, and combine these things. And so now at every time step, I have my original velocity channels here. I'm combining it with, this is the internal flow of those velocity channels, and then I'm combining it with the inverse of my action flow. I've moved up, so we flow everything down. And basically what this yields is this equivariance to self-action and action of the external world. So here's the example of the model on flowing MNIST. You can see the true world with the observation window. This is the ground truth view. This is our model. This is our model without velocity channels. This is without the self-motion equivariance. And this is a diffusion forcing transformer, which is like closest state of the art in terms of world modeling with memory. And so that wasn't super clear, but we have a static version here, and you can see that the diffusion model, since it doesn't really have a notion of long-term memory, it just has like a fixed context window of memory, it eventually just loses track of everything and starts hallucinating digits. Whereas our kind of full model is able to track the state up till the very end. People have also tried to augment these models with recurrence, and still it's not able to track this motion outside the field of view. Again, we learn super fast compared to without these equivariance properties, and we again get this length generalization. So this is our model, and then this is the diffusion forcing transformer model. And you can see it actually does worse than the all black baseline on MNIST because it's just hallucinating random digits that are not there, and it comes from the strong diffusion prior that these models have. Okay, then we wanted to test this on 3D environments, right? Because it's much more interesting than 2D. And so the idea was, let's build a task where you're a little agent in an effectively kind of simple world. You're moving around and there's these blocks that are moving back and forth. It's kind of like crossing the world's most insane intersection. And you can see this was what the agent would actually see in that world. And these were the observations that we provided to the agent. So it's pretty crazy. I'm honestly surprised that any model could solve this. But in order to do this, we needed a much more powerful encoder and like recurrence operation than we had in this RNN version. So we showed that you can just generalize the flow equivariance property to any kind of arbitrary recurrence operation that's denoted by U and an encoder denoted by E, as long as these parts are both equivariant themselves. So for example, we use a vision encoder for E, a VIT, a vision transformer, and used this like update write operation for U, and we proved that these things are equivariant, so the whole thing is flow equivariant. I'm not going to go into this model in detail, but fancy vision transformer tricks to basically train a transformer to map from 3D to a 2D top-down map, completely unsupervised. The only thing we're doing is flowing these latent channels, and we see that the model learns to do this map and then can generalize. So what does that look like? Again, we're showing the world here, agent view. The yellow square means that we're, the yellow outline means that we're in the observation phase, where the agent is actually getting the world observations. When that disappears, we're in the prediction phase, where it's only getting its own action. So now that's where this begins. And we can see already these models are starting to accumulate error of block positions. And then as we go even further, they basically just start to hallucinate blocks that aren't there. Whereas our model can roughly keep track of all the blocks up until the very last frame. So that's the extent of the results we have so far. Planning to use this on more things. If people have ideas, please reach out. Because this is a physics colloquium, I wanted to share how this might be used for not just these Galilean transformations, but maybe more practical, useful space-time transformations for physicists. So for example, you can extend this to Lorentz transformations. The difference here is that you need to keep a history. You need to keep like a buffer of your input, because when you do the Lorentz transformation, you're mixing the past into, or the past into your future in the hidden state. You do this tilt operation. So the basic idea is, instead of just having the input, you now have a buffer which has a sequence of time up to -L. You have these operators that operate on your hidden state and your input, which we need to be Lorentz equivariant. Like I said before, the group equivariance. Your hidden state is now augmented with a boost dimension rather than a velocity dimension. You're lifted to the Lorentz boosts. we need our, like I said, we need our operators to be Lorentz equivariant, so we build them as these polynomials of wave equation. Wave equation is Lorentz covariant. You can build your convolutions, your input, and your hidden state updates this way, and it'll commute. And then your flow operator looks like a Lorentz spoof. Okay. That's all I'm going to say about that. If you're interested in it, please come ask me. I think there might even be better ways to do this. And I know people have built Lorentz equivariant transformers and things like that. So this is not the only way to do this. There may be better ways. I just wanted to throw that in there. So with that, the last few minutes, we're going to talk about something I've heard I was allowed to give a very speculative idea or claim here. So here we go. Traveling waves in the brain are something that I've been very interested in for a while now. This is the Kempner Institute, so we're interested in neuroscience and machine learning in the intersection. This work was all about kind of like machine learning theory, but traveling waves are something that have been seen throughout the brain in a variety of contexts. So this is global waves at a very slow time scale across not even just regions of cortex, but cortex, striatum, thalamus simultaneously. This is at the very smallest, fastest time scale. This is in visual cortex of a monkey. They're shown a really bright stimulus. I think they're doing voltage sensitive dye recordings here, and you can see that there's a bump that kind of propagates outward as a single trial level. There's another kind of pretty interesting and well-known paper showing that in visual cortex of marmosets, little monkeys, they recorded waves that are traveling over area MT, this motion-sensitive area. And basically, they showed that as these waves pass over that area, if you align your stimulus such that it hits right when the peak of the wave is over the corresponding area, the monkey is able to better detect that stimulus. You can see this is a visualization of the recording from this electrode array. And people have hypothesized a bunch of different functional roles for these traveling waves, right? Maybe they transfer information, maybe they modulate visual processing, they're sequencing operations, maybe they're structuring cortical space, maybe they're encoding motion, memory, blah, blah, blah. Ton of different things, but it's relatively debated. There's not a lot of consensus in the literature. Moses has a great paper on another role of waves, if you're interested. But I think the one that's interesting and relevant to this is that traveling waves have been linked in some studies to the encoding of motion. So one example is this paper where they showed that there's this visual illusion where if I show you a dot and then I show you a bar, you'll perceive it as something like that dot grows into a bar, but only if I prime you with that dot first. And so what they show is that this is, okay, let me see if I get these correct. This is what the neural activation looks like for, I think this was like voltage sensitive dyes again. If I just show you the dot, there's a bump and then it kind of goes away. If I just show you the bar, there's nothing and then you get like a huge massive activity. If I show you a little bump that moves downwards, you get something that's like a flow. Or sorry, this is not a bump that moves downwards. This is the actual growing bump into the thing. You get this flow. If I just show you this illusion, you again get this flow of activity. So there's a similarity between when you see the illusion versus when you actually see the real thing, and they both kind of look like this flow of visual activity or activity in visual cortex. A second example is, I think, yeah, also monkeys trying to do a visual motion discrimination task, or they were seeing some stimulus that's moving at either 90 degrees or 180 degrees. And basically what they found is that after the stimulus, before the stimulus was presented, the flow field of neural activity was roughly random. After it was presented, there was a clear directionality to how neural activity flowed. And you're able to actually classify which stimulus the monkey was looking at based on the phase field of this flow of activity. So there's some connection here. can we formalize this connection with flow equivariance? That's the exciting part. So my claim is that these traveling waves are really flow homomorphisms. They are, like I was arguing before, I was drawing that commutative diagram. The waves are that latent operator in the hidden state that corresponds to your input transformation. And so you actually have to have these traveling waves for the encoding of motion. It's not that the wave is just helpful for encoding motion or it's just a representation of the motion. You really need to have this wave going autonomously, right? Your hidden state, everything I was showing before, your hidden state needs to flow at the same time as your input in order to get this nice property. So you need to have something that's autonomously flowing, separate from the input transformation, not being driven by the input, in order to get this kind of stable encoding of motion. This is my argument. Traveling waves are doing something like this in the brain. There's a little bit more evidence from neuroscience that I think supports this. I don't know if anyone believes me, but basically traveling waves are believed to propagate along these local lateral connections in cortex, these horizontal connections, at least in visual cortex. They've showed this computationally, and there's some studies that support this as well. This is a spiking network model where they reproduced kind of like statistically similar traveling wave dynamics in a locally connected spiking neural network. These local lateral connections that we think waves propagate over are also known to connect preferentially to neurons that are similarly tuned to each other. So this here we're showing the orientation selectivity of a bunch of neurons and primary visual cortex. This shows kind of like the orientation preference of where you did the injection. They're all mostly on this like horizontal bar. And then here we're showing the connectivity to, or we're showing the orientation preference of where these neurons are connected to. And you can see it's roughly neurons of the same orientation. You see purple is connected to purple mostly, and then a little bit of the other orientations, right? So there's like a roughly like similar orientation connectivity, but it's not just similar actually. It turns out that they're very structured. And these connections, there's some people in this neurogeometry space, these connections form what they call these integral curves of smooth, continuous transformations. So what they showed is that the connectivity is best modeled by lines of constant curvature. So if you imagine here, I'm saying that everything is connected to the same orientation. It's not exactly the same orientation, that's a flat line. It can also connect to something that goes like this, and then another one that goes like this, another one that goes like this. And that's what these plots are trying to show here. So you slowly kind of have this degree of curvature. And this is actually a flow transformation. This is an exponential of a simple the Lie group element. And the argument is that this property is what causes you to have this good continuation perceptual bias. So it's why you see this drawing as looking like this rather than looking like this. You kind of connect lines that have this these smooth curvatures, and there's a lot of kind of psychophysics examples that you can do to demonstrate this. So this is my crazy speculative hypothesis. These waves are kind of supporting the encoding of these kind of smooth transformations, these flows of the actual input. I think there's evidence. Maybe someone will help me test it. So thank you. There's a lot of next steps, obviously. Please reach out if you're interested. And yeah, I hope it was interesting. Thanks for listening. Thanks to all these people who are on the world modeling paper, Elin, Hansen, Ben Hao, Feng Nang, and then everyone here at the Kempner. Moses worked on a lot of this stuff. These people I've all had great conversations with, Demba, Talia, Benshu, John, Sam, Ella, Gaia, who's introduced me, has been fantastic in talking about all of this. And yeah, so appreciate it. Questions?
So there is a microphone in the room, just feel free to raise your hand. Questions.
The models, when you're doing the comparisons between like the flow equivariant models and the comp RNNs, or the normal models, the baseline models, roughly how like, are they parameter number matched? Is it orders of magnitude more? In theory, you know, there should be ability for these RNNs to sort of derive low equivariance, either within single layers or multi-layers. Yeah, how are you sort of thinking about that?
Yeah, no, that's awesome. They are parameter matched because the flow models have no extra parameters when we do this like pooling over velocity channels. Because I think as I was trying to show,
No extra trainable parameters.
no extra trainable parameters because we're sharing parameters over this flow group, right? So these weights are all the same between all the layers, but we have a ton of extra activations here at the size of the group. So some of the other experiments I did were, what if I just add a ton of extra channels to a regular RNN? Can it learn this type of stuff? It does not typically. And I think this is the same as in the equivariance literature. Like, if you want to get these automatic generalization properties where like it's never seen this velocity before, there's no way it could learn that from the data. But I would agree that in theory, it's possible if it sees a lot of data and it has a bunch of channels, one of those channels could learn, if you give it an extra little kind of recurrent operation, it could learn this flow operation in there. The nice thing is building it this way, we know how those flows are going to act on the hidden state. So we can pool over them appropriately and yeah. Moses.
It's like, for example, the putting a voucher thing, for that toy example you showed, there's a very small bar and then the next frame is the entire bar and the brain's supposed to kind of fill in the gap essentially. That looks a little bit like transfer information when there's two distinct spatial regions that communicates.
Yeah, that's a good point. I haven't thought about it. I've thought about it mostly in the memory context. There probably is a way to frame it that way. In the memory context, I think you can frame memory as like a symmetry over time, like a flow over time. So there's a way of thinking of those models because the other models that I built for long-term memory and RNNs turn out to be very similar to this model. For transfer information, probably I would, yeah. I mean, yeah. Yeah, we should talk about it. That's a good question.
There's a question on Zoom.
Oh, okay.
If you can unmute and ask the question, I think they can. That's-
Do you want me to unmute the person?
I should be able to unmute themselves.
Hi, can you hear me?
Yes.
Thanks. Thank you for the talk. So I have two questions about the model. First, could you generalize to the case that the generator of the flow is itself time dependent? And so it's not constant velocity, it has acceleration. And also, could you make some comments on using a steerable convolution instead of the group convolutional network?
Yeah, perfect questions. Thank you. I mean,
Sure.
those are
Thank you.
both, yeah, both things that I would love to be able to do and have not done yet. I'm trying to bring up the equation again here so I can point at it. How do I get rid of this window? There we go. Yeah, so the velocity, the changing velocity thing, formally flows in order to get the flow composition property that I was talking about, where time t plus 1 is equal to t plus 1, right? You have to have a constant Lie algebra element. So your vector field has to be the same and your flow has to be a constant velocity. However, what we observed in practice is that because this convolution in the hidden state is actually mixing the velocity channels, it's doing a convolution over the new as well as the spatial dimensions. It can effectively learn if there's a predictable transformation in velocities, like two objects bounce off of each other or something like that. So it sees the collision happen and then things move. It can learn to transfer activation through different velocity channels in order to model that. So that's the one way right now that we can handle variable velocities. I think there might also be a way to do it in terms of like separating it into coupled equations, where one is like the time derivative of the other. Haven't formalized that yet, but I'm interested in it. The second thing with steerable equivariance, it doesn't apply directly here the way that it's been done previously. But I think there may be a way to do it by effectively thinking of your not having a copy of your hidden state for a bunch of different velocities as we have here, but actually, if you think of like a real fluid medium, different frequencies will travel at different velocities through that fluid. So there's like a dispersion relation and things like this. I think you can build a recurrent neural network that leverages this to simultaneously move information at all velocities. And so I was playing with this a little bit, and I built so like a wave packet has a group velocity to it, and that group velocity is a function of the frequency of the spatial frequency of that wave packet. And that has a corresponding oscillation frequency. And so when you change that spatial frequency, that wave packet moves at a different velocity. Anyway, all I'm saying is that I think there's a way to do it, and it's kind of related to the steerable stuff, but I haven't fully figured it out yet. So if you want to talk about it, please send me an email, and I appreciate it. And
Thank you so much.
thank you.
Can I ask a question quickly?
Sure, yeah.
So, like, one of the things that attracts me about this model is that because you decouple in different velocity, you sort of build in some sort of interpretability in the model. So depending on which filter your data essentially trigger, you could tell what velocity the signal is going to. Have you thought of using this as a way to extract signal or decompose different patterns in time series? For instance, like noisy effects versus signals that maybe are static.
Yeah, that's a great question. I'm trying to get back to slides where I had that. I haven't really, because I guess this is like a really clean example of it, where like the activation is mostly centered in a single channel. But in a lot of cases, like, can I actually like get back here? Like this case, for example, this is another moving input example, but the activation is spread over all of these velocity channels. And really you just get the corresponding shift operation. Like the latent operator that I showed you is the thing that allows you to leverage the kind of flow equivariance property. I think through learning, you end up getting something that's more like this most of the time, especially with that max pool operation. So I think you could use it for something like that. I just haven't looked into it too much yet, but yeah. I think it is interesting because one thing I wanted to mention is like potentially using this for not visual sequences, but other sequences like language or something like that. And maybe if you build in a bunch of different flows, then you'd be interested in a language sequence, like what is the current transformation that this sequence is undergoing. Yeah, it's interesting. I have not worked on it at all, but thanks for suggesting.
More questions?
I think I've wasted everyone's time enough. I appreciate
Question is just thanks, Andy, again for the wonderful talk. So just another one. And we're just transitioning the mixer